So one day I was having fun with Python's pygame library, which allows you to simulate sprite movements on a screen. I wondered to myself, could I try to simulate chemistry with Python? Well, after researching sprite collisions in pygame, I came across this cool illustration of coloured balls spawning and bouncing off of each other. Chemistry didn't seem like a big leap from there. Copying the code and combining it with some previous pygame code, I changed it a bit to allow nitrogen and oxygen atoms to bounce off of each other. I encountered a slight problem. My atoms were sometimes deciding to stick to each other. They were colliding with each other a second time, inverting their velocities and therefore sending them back towards each other. I told them to politely ignore each other if they had just collided, which they actually listened to, although now some of them seemed to hug the walls instead. A short fix later, I tried a bit of transmutation. When a nitrogen and an oxygen atom collided, they'd form a fluorine atom. I guess that this is more nuclear chemistry, but without regarding any conservation rules. I then proceeded to make the collisions elastic, i.e. conserving the momentum of the nitrogen and oxygen atoms during collisions, as well as sizing the atoms correctly. Some of the atoms were wandering off the screen into the abyss, which I shortly corrected, and at this point, my elastic collisions meant that the speeds were Maxwell-Boltzmann distributed. This is the natural distribution of particle speeds for ideal gases. I then introduced diatomic molecules, so that a nitrogen and oxygen molecule would collide together to form nitrogen oxide, i.e. actually doing chemistry now. Then I made some water from hydrogen combustion. Because the collisions are elastic, something interesting happens. The very low mass of diatomic hydrogen means that, for a given change in momentum, its velocity changes significantly. Therefore, the moderate momentum of the oxygen molecules, due to their moderate mass, is gradually turned into a very high velocity for the hydrogen molecules. I should note that these sorts of reactions, involving at least 3 reactions, generally proceed stepwise via radical intermediates with unpaired electrons. However, I'm just keeping it simple here. I've also made the whole sequence from N2 and O2 to NO2 via NO. You can see that the reaction forming NO2 from NO starts to slow down, which is due to the low number of oxygen molecules. This makes it difficult for 2 NO molecules and an oxygen molecule to collide with each other simultaneously. At this point, I am able to delve into chemical kinetics. To start with, I can have a first order reaction, such as the theoretical unimolecular decomposition of NO2 into NO and oxygen. According to the first order rate law, this reaction should proceed with a linear drop in the natural log of NO2 concentration with time. There are enough molecules for this to indeed be the case. The rate constant, K, is the negative of the gradient. The calculated value is quite close to my specified value of 0.04 seconds to the minus 1. For a second order reaction, I could use the breakdown of NO back into nitrogen and oxygen via NO collisions. This proceeds with a linear relationship between the reciprocal of NO concentration and time, with the rate constant equal to half the gradient. I also implemented reversible reactions with a tunable equilibrium constant and activation energy. There are two ways to set up an equilibrium. You can do it probabilistically by comparing the temperature, i.e. mean molecular speeds, to the activation energy. This approach somewhat worked. Alternatively, you can calculate the energy of each collision and compare this to the activation energy. This approach also somewhat worked, but not entirely. One further thing to try were Arrhenius plots. The rate constant can be defined by A multiplied by E to the power of minus EA over RT. Taking logarithms, this gives ln K is equal to ln A minus EA over R times 1 over T. Therefore, plotting ln K against 1 over T should give a straight line with intercept ln A and gradient minus EA over R. However, this does only work at low conversions when the reaction is kinetically rather than thermodynamically controlled, i.e. the rate of the reverse reaction is negligible. To obtain this, I ran the simulation at temperatures between 220 and 320 Kelvin, i.e. minus 53 to plus 47 degrees C, getting K at 20% conversion. So that the reactions were more probable, I had to use a quite low EA of 5 kJ per mole compared to e.g. 75 kJ per mole for hydrogen peroxide decomposition. Nonetheless, although there was no particularly strong linear fit, it gave an EA value of 4.8 kJ per mole, which I'd say is close enough. So, can you do chemical kinetics in Python? You sure can, but just don't add too many molecules. But if you do want to do your own chemistry, I've left a link to my code in the description, including an explanation on how to set up the simulation. Thanks for watching, and I hope you enjoyed and learned something about chemistry.